Rose, Assistant Professor, St. Albert's College, Ernakulam. Today, I'm here to introduce you to the topic, the KONIGSBERG Bridge Problem, an Introduction to Graph Theory. Graph theory is a branch of mathematics which came into action once the problem, KONIGSBERG Bridge Problem, came into. So let's see what this KONIGSBERG Bridge Problem is and what the solution of this problem is. So before going into the problem, can you just pause and answer this question? The question is, there are 4 land masses and there is a river flowing through this. 1, 2, 3 and 4. 4 land masses, that is land, and there are 7 bridges connecting these lands in some or the other way. That is 1, 2, 3, 4, 5, 6, 7. There are 7 bridges. So the question is, are you able to start from any one land, cross all the bridges exactly once and reach back at that place itself? But the only condition is you can travel through one bridge only once. No repetition of bridge is allowed. So you can start from any of the places. You can start from this bridge or any bridge and then reach back at the same position without repeating any of the bridges. Just think. So this is the famous KONIGSBERG Bridge Problem. Actually, this is the city of Konbridge, which was divided into 4 sections by the branches of Pragen River. So the Pragen River, it divided the city into 4 sections and there were 7 bridges that connected these 4 regions. The 4 regions included the banks of the Pragen, Kinlof Island and region between the 2 branches of Pragen, that is represented in this diagram. So the problem was, in 18th century, the people of that town itself, they took leisurely walks through the city and they thought if it was possible to walk through all the 7 bridges and reach back at the same position without crossing the bridge, any of the bridges with repetition. So this was a simple thought that came into people and that discovered the famous graph theory, a topic of mathematics which is still developing. It was Leonhard Euler who gave a solution to this problem. So before going into the solution, let us see some basic definitions about what graph is and what graph theory is. So we are going to define what a graph is. Till now, we have seen graphs denoting a x-axis, a y-axis and a line joining different points. But here it's a bit different definition to graph. A graph is defined as ordered pair v, e, where v is called the set of vertices and e is called the set of edges. Before going into definition, let's see with the example. Here it is an example of a graph. Here the white balls represent the vertices, that is 0, 1, 3, 4 and 5. Just a number given or any alphabets or letters can be used to represent vertices. So here 0, 1, 3 and 4 and 5 are the vertices. And edges is anything that joins 2 vertices or it can be between one vertex itself. Here red letters represent edges denoted by 1, 4. So here 1 is an edge that is associated with the vertex 4 and associated with the vertex 5. Similarly, here the edge 2 is joining the vertices 3 and 1. So graph is simply an ordered pair of a set of vertices and a set of edges. And an edge is said to connect its endpoints. Here the edge 4 is said to connect the endpoints 4 and 0. Some more definitions. First definition is 2 vertices u and v in a graph are said to be adjacent if u and v are the endpoints of an edge in G. That is, 2 vertices of the graph are said to be adjacent if there is an edge joining both of them. So here if we see 0 and 3 are adjacent because there is an edge 3 which have 0 and 3 as the endpoints. Next definition, if E and H associated UV, then HE is called incident with the vertices U and V. That is, if E is associated with the vertices U and V, then the edge is called incident with the vertices U and V. That is, if we see the edge phi, then we can say that phi is incident with the vertex 0 and phi. Also, it is called that the edge is said to connect U and V. The vertices U and V are called the endpoints of an edge associated with U and V. Next, we define what the degree of a vertex is. The definition is the degree of a vertex in a graph is the number of edges incident with it, and it is denoted by degree of V. So, if you take any vertex in a graph G, we will be able to find the degree of the vertex as the number of edges that is incident to it. So, if you take the example of F, we have the edge BF, EF and FG and FC. 1, 2, 3 and 4. 4 edges are incident with F. So, we say that degree of F is 4 in this graph. Similarly, here if we consider V5 we have E2, E4 and E5 are edges incident with V5. So, we say that degree of V5 is 3. So, according to any vertex in the graph, we will be able to find the degree of the vertex. Next, we define what paths and circuits in a graph is. As the name path denotes, it's a way or how you will move from one place to another. So, here a path of length n from a vertex U to a vertex V, it is defined to be a sequence of edges E1, E2, etc. En such that E1 will be the edge associated with x0, x1, E2 will be the edge associated with x1, x2 and so on, and En will be the edge associated with xn, x0, where the x0 is the initial vertex from where we start. X0 is U and xn is the vertex in which we will end, that is V. So, in this example, if we consider, if we have to move from V1 to V3, we can take the path E3, E5. Similarly, we can take the path E1, E3, E6. So, between any two vertices, we will be able to find a path. Sometimes the path may exist, sometimes it may not exist. Next, what is a cycle or a circuit? Cycle, as it denotes, the name denotes, it will start at one point and end at the same point. So, the definition follows: a cycle or a circuit is a path that begins and ends at the same vertex. That is, it will begin at a vertex and end at the same vertex. If we consider E4, E5, E6, it will start at V2 and end at the same vertex V2. Next definition is, what is a simple path or a simple circuit? A path or circuit is simple if it does not contain the same edge more than once. That is, if an edge is not repeated in the path or in the circuit, it is called a simple path or a simple circuit. The example which I said before, V2, V3, if we go from V2 to V5, E6, E5, it is a simple path because edges are not repeated. If we are going from V2 to V2 itself or V2 to V3, if we go by E6, E5, E4 and E6, the edge E6 is repeated, so it is not a simple path. So, no edge should be repeated. Next, we define what a connected graph is. A graph is called connected if there is a path between every pair of distinct vertices of the graph. That is, for any pair of vertices we take from the graph, we should be able to find a path connecting those two vertices. So, As the name denotes, it should be connected, that is, it should be as one. So here in this example, if we see here A and F, there is no path joining A and F. So this graph is not connected. While as in G1, for any pair of vertices, if we take B and E, we have the path BC, CD, E, or any pair of vertices you take, you will be able to find a path connecting them. Then it is called a connected graph. So here we have G1 is connected while G2 is not connected or disconnected. Next we define what an Euler path and Euler circuit is. A Euler path in G is a simple path containing every edge of G. So the definition of path comes and in addition to that, it should be a simple path. That is, there should be no repetition of edges. So Euler path in G is a simple path containing every edge of G. That is, it should be simple and also must contain every edge of G. Similarly, Euler circuit in the graph is a simple circuit containing every edge of G. That is, a circuit which is simple and must also contain every edge of G. If we consider the examples, G1, G2, G3, three graphs are given. In the first graph G1, if we are able to find a Euler path, that is a path that is going through every edge of G, which is also simple. That is, there is no repetition of edges in the path. If we consider a path A, B, E, C, D, E, A, it is a Euler circuit that starts at A, goes through every edge of G exactly once without repetition and goes back to it. That is a Euler circuit because there is no repetition of edges but goes through every edge of this graph G1. So we can find a Euler circuit which is also a Euler path in G1. While in case of G2, however we go, we will not be able to find a Euler path or a Euler circuit. If you want, you can try it out yourself. However, you travel through the edges, you will not be able to find a Euler path or a Euler circuit. While in this case of G3, you will be able to find a Euler path but not a Euler circuit. That is, we start at one point and cannot end at the same point. You can see it yourself. A, B, E, D, C, A, D and B is the Euler path, but we cannot find a Euler circuit. So given a graph, we should be able to know if there is a Euler path or a Euler circuit. There can be graphs having a Euler path but not having a Euler circuit, and also not having a Euler path or a Euler circuit. So let's come back to our KONIGSBERG bridge problem. How can this graph theory be used in this KONIGSBERG bridge problem? So here we convert our bridge problem in terms of graph theory. The problem is converted in terms of graph theory as the regions representing the vertices and the edge representing the bridges. That is, we had 4 regions, 4 land masses, and there were 7 bridges. We are representing the land as vertices and edges as the bridges connecting them. So there are 4 lands A, B, C and D, and there are 7 bridges, 1, 2, 3, 4, 5, 6 and 7 bridges. And so we have converted the problem into a graph. So now we have to find a way in which we start at one bridge, cross through all bridges exactly once and reach back at that position without repeating any of the edges. So it is exactly a Euler circuit that we have to find in this graph. So is it possible or not? That was what came into Euler's mind while thinking about this KONIGSBERG bridge problem. Is it possible to find a Euler circuit in this particular graph? So, while thinking about a solution to KONIGSBERG bridge problem, it came into Euler's mind a theorem, or he was able to think about how a Euler circuit can be found in a graph, which was given by the theorem. A connected graph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. That is, a graph can have an Euler circuit only if every vertex of that graph has even degree. So that came into the solution of KONIGSBERG bridge problem. That is, when we represented the problem into graph, we got 4 vertices and 7 edges. But while we examine, we see that the vertex A has degree 1, 2, 3, 4, 5. That is, this particular vertex A has degree odd. So that the theorem is violated in that case. So we cannot find a Euler circuit in that problem. And that came into the discovery of graph theory, which is still a developing field of mathematics which has great applications. The applications of graph theory goes into chemistry for the construction of bonds and study of atoms. It's also used in sociology. Graph theory is used in biology and conservative efforts, and planning and scheduling of large complicated projects, and it is applied to the problems in engineering, economics and war science to find optimal way to perform. It is also used in computer science, which has great applications in networking. Thank you and have a nice day.